Alright, hello everyone. Today our group will be presenting our project on wave energy systems and their connection to the chemistry industry. Our goal is to show how wave-powered buoys work, what we discovered during the boat trip, and how chemistry plays a major role in keeping these systems working effectively in harsh ocean environments. So, what is this project about? This project investigates how wave energy converters can power offshore buoys, especially in coastal regions like the ones we visited. These systems depend heavily on chemistry because they operate in salt water, which constantly reacts with the and materials used in marine technology. We also explore how chemical principles like corrosion, ion movement, and material durability are directly related to the performance and lifespan of these buoys. Understanding this connection helps us see how chemistry supports both renewable energy and coastal engineering. So, our team duties and agreements. Our team has 4 members: Isaac, Zach, Koa, and Nathan. So, we each had clear roles. Uh, I handled the intro and the slide flow. Zach covered the boat trip and coastal chemistry. Koa explained buoy chemistry and the literature. And Nathan will be presenting the solutions and references. So our main challenge was connecting an engineering topic to chemistry clearly. We overcame that by making a shared outline, assigning specific roles, and cutting unnecessary details. Our agreement definitely helped keep the work balanced and made editing easier. At first, we suggested different ideas like corrosion, pollution, and battery chemistry, but we chose wave energy buoys because it was the strongest connection between chemistry and what we saw and experienced at the boat trip.
Howdy. My name is Zach, and so our boat trip findings were that on the boat trip we examined several coastal locations that showed real world examples of chemical processes happening in the environment. So at the SS Selma site, we saw severe corrosion on the structure, and at Pelican Island there was metal components on the bridge that showed oxidation. And then the cruise terminal and the shipyard featured like machinery components that were constantly exposed to salt and moisture. So these are real world examples which helped us understand how coastal chemistry affects materials over time, and especially in places with a lot of salt and moisture. Um, so for our the chemistry behind our observations was we like what we observed on the boat trip directly relates to the chemistry happening in saltwater environments. Saltwater acts as an electrolyte, which speeds up oxidation on metal surfaces, which leads to corrosion, rust formation, and material weakening. We also saw signs of galvanic corrosion, where two different metals corrode at different rates when they are in contact. And then these processes are all electrochemical reactions, specifically redox reactions, involving the transfer of electrons. And then understanding these reactions is important for us because wave energy buoys, they face these challenges every day.
um, Wave energy buoys depend heavily on chemical principle because they operate in salt water, which is one of the most reactive environments on Earth. Salt water acts as a strong electrolyte, meaning it speeds up a mechanical reaction on the metal surfaces. This makes the corrosion a major challenge for any buoys or marine device. To survive a long term, these systems require corrosion resistant alloys and protective polymers coating that physically block ions like chloride from reacting with metal inside inside the buoys. Chemistry also plays an important role through electrochemistry because the electricity generated by waves must be stored efficiently. So overall, chemistry determines how long a buoys can last and how stable its power system is and how well it performs in harsh coastal environment. Without understanding these chemical processes, wave energy systems simply wouldn't function reliably. The, the scientific literature strongly confirms the chemical challenges we see in the marine energy systems. Studies from NREL and other sources show that the chloride ions in the seawater significantly accelerated oxidation and corrosion on metal. Research also explains that higher ocean temperatures, increasing acidity, acidity make corrosion faster and more aggressive, which matches what we observed during our boat trip. Um, Other sources highlight how degrading metal release ion and particle into water, which can interact with marine organism and biofueling layer. This shows that corrosion isn't just an engineering problem, it's also a chemical and environmental one. Finally, the literature supports the solution used today, such as polymer coatings, anti-fouling chemicals, and sacrificial notes. These methods are grounded in chemical principles and help the wave energy devices survive the long-term effects of saltwater corrosion.
3, 2, 1, we're starting. All right. So, thank you, Khoa, for being the one before me. And my name is Nathan. So, how does chemistry help engineers in the project of bringing boys? Well, simply put, it allows for preventing coatings of slow corrosion, which means that it will allow us to help protect the marine structures that we build. Of course, we can also use polymer coatings, and that will also be able to allow us to block corrosion. And anti-fouling chemicals prevent marine organisms from growing on the buoy surfaces, making it easier to collect data as well as be able to study it. More things, and we aren't going to have to deal with these inevitable seaweed. Additionally, we can just simply improve our battery chemistry. Improve battery chemistry, the battery lasts longer, it works for some reason. And that means that by applying such chemical knowledge, engineers can design systems that last longer. We engineers can design systems that last longer, that require less maintenance, and that work effectively in saltwater environments and other extreme hazardous environments. Why does this not work? Anyway, the proposed solution, as discussed from the above points and the points that Khoa made, is that we can combine wave energy systems with the proposed chemical protection systems in order to make it better. This also allows us to use polymer coatings and sacrificial anodes, which allow us to absorb corrosion before it reaches the most important parts. And that means that we can make it last longer. This allows us to use materials that will be able to perform more and collect more data in these harsh marine conditions. We can also use improved battery chemistry because, again, a longer lasting battery means that we can collect more data, and that means that we can prepare and be absorbed for more dangerous situations. Finally, these are our references. These come from the US Energy Information Administration, NREL research, to wave energy, engineering databases, and our own boat trip observations done by, I believe, Isaac. These references help us collect chemistry concepts and allow us to correct our misunderstandings, while there were many, and would allow us to improve our engineering applications. Thank you for listening. Do you have any other questions? Additionally, these are links to the sources itself. Thank you.